Hi everyone, today's topic is going to be on the pH scale, so please take out your notebook, your reference table, and something to write with so that we can get us started. Today your main focus should be on being able to identify pH values. So pH values range from 0 to 14, and you need to know which parts of that scale fall as acidic, neutral, and alkaline. Alkaline is a fancy word for a basic solution. What you should do today is the Canvas quiz due now. You should be able to find it in the module for this week. And then right now we're going to take pH scale notes. The first thing that we're going to go over is the different strengths of acids and bases. Strong acids, and bases for that matter, are ones that completely ionize in water. This means you go from the compound completely just to the ions in solution. Here is an equation representing that. So we have hydrochloric acid plus water breaking down into hydronium ion plus chlorine ion. Remember, hydronium ion is one of our representations of H+, so essentially our acid has completely broken down into its ion components. Weak acids are not going to completely ionize, they're only going to partially ionize. This means there's going to be less hydronium ions in solution. Our equation representing this has a new symbol, as you can see right here, these double arrows. This means that you have a relationship between our compound and our ion, so it's continually breaking down from this compound, our acid, to its related ions, and vice versa. These ions will then reform back into the compound, so there's always a little bit of compound, always a little bit of ions. We'll talk a little bit more about this symbol later on this year. Strong bases, like I mentioned before, ionize completely in water. This means you take a base, something with that hydroxide ion, add it to water, and it's going to completely dissociate into its ions. So in this case, potassium ion, and then our hydroxide ion. Weak bases, same concept as weak acids. They're only going to ionize partially. This means we have less hydroxide ion in solution. And here is a representation of that. We have ammonia added to water. It continually breaks down into ammonia ion and hydroxide ion, and then is reforming NH3. Basically, these arrows, we can read this equation frontwards and backwards. Water self-ionizes. It's a unique property of water. What this means is that when you have water, it is continually breaking down into H+, or hydronium, H3O+, and hydroxide. Eventually it reaches what's called an equilibrium, basically a balance between water as a compound and our hydronium and hydroxide ions. We'll talk a little bit more about this term later on this year. The important part to understand is that it produces the same amount of hydronium ions and hydroxide ions. In fact, as you can see from this equation, we have 1 mole and another mole. This means when you have the same amount of hydronium and hydroxide ions, you have a perfectly neutral solution. pH is going to be 7. pH of 7 is neutral. Water is usually the most common example of a neutral solution. Moving on to pH scale. So one of the important things about pH, and what makes it a little bit more complicated, is it's a logarithmic scale. Some of you might have talked about that in algebra already. But what this means for us is that 1 unit difference in pH is equivalent to a 10 times change in amount of hydrogen ions. I guess I should back up really quickly. When you see pH, this H is standing for hydrogen ions. So pH is directly related to the concentration of hydrogen ions. Another representation of concentration is to put a bracket around whatever you're talking about, and this means concentration of hydrogen ions. And again, 1 unit of difference means a 10 times change in concentration. A couple things that you need to have down is pH less than 7 is acidic. That means the solution has more hydrogen ions than hydroxide ions. pH of 7 is neutral, just like we saw with water, has equal amounts of hydrogen ions and hydroxide ions. And a pH greater than 7 is basic or alkaline, meaning it has less H plus ions and more hydroxide ions. Continuing with some examples about pH scale, just to reiterate the fact that the concentration is a 10 times change with each unit change. If we have a pH of 7 compared to a pH of 8, 7 lower on the scale is going to be more acidic, but it is 10 times more acidic than a pH of 8. So again, 1 unit of change is a 10 times change in concentration of H+. If we have a change of a pH of 4 to a pH of 2, that solution is becoming more acidic because we're going from 4 to 2. And because we have 2 units of change, this indicates 100 times change in hydrogen ion concentration. So we go 10 times 10, 10 factor change for each unit that changes. So if we change 2 units of pH, 100 times more hydrogen ions. Last example, if we change from a pH of 8 to 12, now we're getting more basic. If we go from 8 to 12, we have a 4 unit change. 10 times 10 times 10 times 10 is 10,000 times, which means when we change from pH to 8 to 12, it is now 10,000 times less hydrogen ions, 10,000 times less acidic than the original solution. What I would like you to do is pause the video and actually copy down this chart before I start explaining it. As you can see, this chart shows the relationship between the concentration of hydrogen ions, this right here, concentration of H+, and pH. So all of this is based on HCl, hydrochloric acid. When we have 1 molar hydrochloric acid, it's going to completely ionize, we're talking about a strong acid, into 1 molar H+ ions in solution. If we put this into scientific notation, we get 1 times 10 to the 0. So our concentration of H+ is 1 times 10 to the 0. This right here, our superscript on the 10, gives us our pH. So if this is 1 times 10 to the 0, we have a pH of 0, very strong acid. If we have a 0.1 molar hydrochloric acid solution, this is equivalent to 1 times 10 to the negative first in scientific notation, which is equivalent to a pH of 1. So we're essentially ignoring the fact this is a negative 1, looking at the superscript, pH of 1. If we continue to fill out this chart and we have 0.01 molar, we end up with 1 times 10 to the negative second for our concentration of hydrogen ions, which is a pH of 2. And continuing on that thread, if we have 1 times 10 to the negative third concentration of hydrogen ions, that is a pH of 3. And lastly, I just wanted to give you some reference points for pH. So starting from very acidic, a pH of 0 would be something like battery acid, specifically battery acid from a car battery, not so much from like a AA battery. Acidic stomach, so if you have an upset stomach, it usually means your pH is slightly off. We fix that with antacids, right? Which are over here on the basic side. Lemon juice, pretty acidic. Soda, hydrochloric acid, pretty acidic. For example, Coca-Cola is acidic enough to take rust off of stuff, so it is fairly acidic. Orange juice, coffee, a lot of the things that we eat and consume fall into this acidic range. Rain tends to be slightly acidic. Water, our neutral compound. And then just some other cleaners, lye being like pure drain cleaner, very corrosive, dangerous to get on your skin. Both the extremes of either side of the scale are damaging enough to burn through your skin. Most of what we deal with tend to be in this middle range. I would suggest that in your notebook you copy this down, even color code it according to the scale, just so that you get a better grasp of pH of common substances.